All right, here we're looking at section 10.1. And our learning targets for today, first we're going to be graphing square root functions. Then we're going to compare square root functions using average rates of change. And we'll talk about some average rate of change, what that really means. And then we're going to look at solving some real life problems using square root functions. Okay, so we always, when we're talking about these families of functions, right, we always start with our parent function, which is the most simple we can get. And here we're looking at square root functions. So I'm looking at the square root of x. Okay, so here you'll see the graph of my parent function of the square root of x. So I know when I have 0, the square root of 0 is 0. When I have 1, I know the square root of 1 is 1. Then I can continue to go up. If I plug in 4 for x, I know the square root of 4 is 2. And I can continue. Again here, the square root of 9 is 3. So I can plug in those values that I know and can draw my graph from there. One thing to notice, though, is my domain and range, right? The domain of my parent function is x is greater than or equal to 0. And we can know that because I don't want to have any negative numbers in here. I cannot take the square root of a negative number. So my domain is limited to x is greater than or equal to 0. And then we also see that my y is greater than or equal to 0 as well. So that's the domain and the range of my parent function. So now here let's look at the domain of f of x equals 3 times the square root of x minus 5. So since this I know cannot be negative, this is called the radicand. The stuff that's underneath my radical sign is the radicand. Since that cannot be negative, I have to set what's underneath my radicand. I have to set that radicand greater than or equal to 0. So all I have to do is write my inequality for the domain and then add 5 to both sides. So my domain for this function would be x is greater than or equal to 5. Okay? And I can do that for any radical function. I just take whatever's underneath my radical sign and set it greater than or equal to 0. So now let's graph this function and then describe the range. Okay, so I want to use my domain as being greater than 0, so I can pick some values that I know to make my table. So when I plug in 0 for my x, I get 0 plus 3. If I plug in 1, the square root of 1 is 1, plus 3 is 4. If I plug in 4, the square root of 4 is 2, plus 3 is 5. If I plug in 9, I know the square root of 9 is 3, plus 3 is 6. And then if I plug in 16, the square root of 16 is 4, plus 3 gives me 7. So now that I have this table of values, I can go ahead and plot those points, and we'll see what my graph looks like. And so then I just draw my curve through the graph. So I can see, based on this graph, that my range is y is greater than or equal to 3, because that's the lowest point on my graph. So now here I want you to think about a couple of these. First, we're looking at the domain. And remember, when we're looking at the domain of these functions, I always want to look at the radicand, the thing underneath the radical sign, and put that greater than or equal to 0. So then these numbers 4 through 6, I'm going to first graph them by picking some x values and then just solving and making a table of values. And then from there I can look at the range. So here's our big piece of information from this chapter, from this section, okay? And this should look very familiar. We've seen these before, we've done this before. So we can have different transformations of our function, right? The first one we can have is a horizontal translation, right? And that moves left or right. Again, this h value we've seen. The h is inside with my x. And remember that if I have x minus 2, I end up going 2 units to the right, because my parent function is always that x minus h. My second transformation is a vertical translation, which goes up or down. And that's where my k value is out here behind, so I can move this up 7 or down 1 in this example. I also have a reflection. I can reflect my entire graph over the x or y axis. Okay, so we see if this negative sign is inside my radical, it will flip it over the y-axis. And if it's outside, out front, it'll flip it over the x-axis. I can also have my vertical and horizontal stretches and shrinks, right? And we've looked at these before. And just keep in mind that where things go and if they're horizontal or vertical. Remember, horizontal things go inside with my x, and vertical transformations, like this translation or the stretch and shrink, go outside, and they deal with the entire function. So here we're going to graph negative the square root of x minus 2 and then compare it to my parent function. So the first thing I do is I go ahead and find my domain, right? And I know that x minus 2 has to be greater than or equal to 0. So then I solve for x, which x is greater than or equal to 2. Then I can pick some x values that fall in that domain and find my y. And then I have my points, so I can plot those ordered pairs and then draw my smooth curve through them. So now I can compare this to my parent function. So the things I notice is here I have this horizontal translation 2 units to the right, and this negative sign tells me that I'm reflecting it over my x-axis. So I can do both of those things. So now here are some that I want you to think about. Biggest thing is think about how I would compare this to my parent function. What have I done to my parent function? Okay, so now here's our next example. So g of x equals negative 2 times the square root of x minus 3 minus 2. First I have to describe the transformations, how it's different than my parent, and then graph it. So the first thing I notice is I have this h value, right? So this h will translate it 3 units to the right. I have this 2 value here in front, and so I know that that is a vertical stretch, so I'm stretching by a factor of 2. This negative sign here tells me that I'm going to reflect my graph in the x-axis. And then I have this negative 2 here, which tells me I'm going to move my graph vertically down 2 units. Okay, so now I can look at my, find my domain by taking what's underneath the radical sign, my radicand. X minus 3 is greater than or equal to 0 and solving for x. So I know x is greater than or equal to 3. So now I pick some x values that are greater than that, and I plug them in, and then I can solve for my y's. And now that I have those points, I can go ahead and plot them. Here on this graph, you can see all of the different transformations, right? So my first transformation was this red one, this h, which kind of moved it, translated it 3 to the right. And then I stretched it, right? Oh, and then I stretched it. I'm sorry, this black one was my first one. Then I stretched it, and then I reflected it, and then I shifted it down. Okay, so I can look at all of the different things that I've done to my graph. It's kind of nice to see these all in one coordinate plane so you can see each step what has happened to my graph. So now here's one for you to try. Go ahead and think about this. Definitely think about what your transformations are first, and then which points would you pick to help you graph this function. So now here I've got our real world problems. Okay, so the model v of d equals the square root of 2gd represents the velocity in meters per second of a free-falling object on the moon, where g is a constant 1.6 meters per second squared, and d is the distance in meters the object has fallen. The velocity of a free-falling object on Earth is shown in this graph. So now I'm supposed to compare the velocities by finding and interpreting their average rates of change over the interval from d equals 0 to d equals 10. Okay, so to find the average rate of change, I want to use specifically the 2 points that I'm told. So I'm told my coordinates are going to be at 0 and at 10. So the first thing for Earth, I estimate by using my graph when I have my x value of 0, which was approximately 0, and my x value of 10, which we were estimating to be about 14. So here's my average rate of change on Earth. So I take the v's, the y's, right? Here I'm finding the slope between these 2 points. So I've got the change in y over the change in x. So 14 minus 0 divided by 10 is 1.4. So now on the moon, I'm going to actually use my equation when d equals 0 and when d equals 10. So I plug in those values. So when d is 0, my v is 0. And when that d is 10, my v is 5.7. So now that I have this, now I can go ahead and use those 2 points to then find the average rate of change, right, by taking the v of 10 minus the v of 0 divided by 10 minus 0, and I get approximately 0.57. So here I can say from 0 to 10 meters, the velocity increases at an average rate of about 1.4 meters per second per meter on Earth, and about 0.57 meters per second per meter on the moon. So now I've compared those, so you see that my average rate of change was much greater on the Earth than it was on the moon. So here's another thing that I want you to think about. Go back and try and figure out if you can find the average rate of change from this interval. So here's another world problem. So the velocity of a tsunami can be modeled by this function. V of x equals the square root of 9.8 times x, where x is the water depth in meters. So we're going to be using a graphing calculator, or you can use Desmos to graph our function. And then we have to figure out at what depth does the velocity of the tsunami exceed 200 meters per second. Then figure out what happens to the average rate of change of the velocity as the water depth increases. So the first thing I want to do is I want to graph my function, and here you can see it on a graphing calculator. You could certainly also use Desmos. Okay, so then we want to use either the trace feature or using Desmos figure out when is my y value 200. Right, and here you'll see I used my trace value, so I see my y is about 200. My x is 4,082. Okay, so that answers that first part of the problem. So now I want to calculate the average rates of change over the interval that I was given between 0 and 1,000. And then from 1,000 to 2,000, and then from 2,000 to 3,000. So we're going to see what happens as my x value gets deeper. Okay, so first I have to find my average rate of change from 0 to 1,000 by plugging in 1,000 into my equation and 0. And then I can do the same with 1,000 and 2,000, plug those in, find my rate of change, and then do the same from 2,000 to 3,000. So now I can see that as my water gets deeper, right, my average rate of change gets slower, or my change in velocity decreases, because these numbers get smaller as my water gets a little bit deeper. So now here's what I really want you to think about. So at what depth does the velocity of the tsunami exceed 100 meters per second? Think about what you would have to do from that last problem to answer this one. So let's look back at our learning targets for today. First, we needed to graph square root functions. Then we compared those square root functions using average rates of change. And right, we always want to look at different intervals with our average rates of change. And then finally, we looked at some real-life problems involving square root functions. When we're graphing these square root functions, don't forget your a, h, and k values. And we've talked about these many times with every family of functions. And they do the same thing with this family of functions as well. So that's always going to be your first step, is determining what transformations have I dealt with and what am I doing with this function. So now that we've looked through these learning targets, go ahead and work on your homework for 10.1.